Hello, this is Concrete Path. Here is the second lecture for your geotechnical engineering that we name it as soil water soil water characteristics, characteristics, soil water characteristics. So we have the soil, we have the soil here, we have the soil here. So it's composed of soil solid particles. You can write soil solids, and we are having that water also, and we might be having air also. So those voids are those voids, they are taken by either water. It can be partly taken by water, it can be having some sort of air also, or it can be entirely composed of air, or it can be entirely composed of water. Then to have a better understanding of the soil, we have what we call as block diagram. We have that what we call as block diagram, and that we also called as phase diagram. Phase diagrams are used to understand and calculate the important parameters related to that soil. So we are going to use this one to simplify our understanding. It simplifies our understanding of that soil. That's in the calculation and understanding of those concepts. So it simplifies that. So we have that block diagram. That let's say that we have a general perspective of the soil. I would say there is some soil, soil solids. We can write here, we have these solids. We can write the soil solids. Soil solids are placed here. After that we can have water. After that we can have air. Here the configuration is that we are keeping the soil solids below. That means they are actually having more unit weight. They are having more weight as compared to the other ones. Their specific gravity, their unit weight is more. After that we have weight of water, and finally at the top we can place the air. So this is what we call as general phase diagram. This is a phase diagram, and we are having three important constituents, so we can write it as three-phase diagram. Now this is a general common observation of the soil. That means you go to somewhere outside, you would take a soil, you would see these three in the soil itself. General common observation. Now I would say your soil, if there is this configuration of the soil, I would say there we have solids. Let's represent the soil solids by S, water by W, and air by A. So I would say there is some weight of the solids associated with it. There's some weight of the solids. We have some weight of the solids. We have some weight of the water also. We have some weight of the water. And we have some weight of the air also. We have some weight of the air. And we say that air is having zero weight. So weight of the air is zero. That's almost equals to zero, we can write. So weight is for the air, we write weight of the air is zero in the soil. And from this side we show the volume of the soil. Volume for it related to the soil. I would say this is the volume of the solids. This is the volume of the solids. And this is the volume for the water. And we say that there is volume for the air also. So air is going to take some volume of the soil mass. If there is some soil mass, you have this soil mass, it's having some pores, and in the pores there might be air or there might be water. So I would say this is the total volume. This is the total volume of the soil. So we write total volume of the soil with that capital V. So this is the total volume of the soil. And from this side I would say this is the total weight of the that soil mass. So let's represent those. Let's denote those. I would say this is the W is the total mass, total weight. We can write total weight of soil mass. And W is the weight of soil solids, weight of soil solids. And WW is the weight of water in the soil mass. And after that we have volume of S, that is volume of soil solids. We can write directly because we are talking about soil, so this is volume of solids. After that we are having VW, that's volume of volume of water, volume of water. After that we have VA, that's volume of air, volume of air. And after that we have capital V, that's total volume of the soil mass, total volume of soil mass, of the soil mass itself, total volume of the soil mass that you are taking, volume of soil mass. And there is one more parameter that we call it as volume of voids. See, there was some soil, it's having some solid particles. There were some solid particles, and between the solid particles there is some space. The total space, the volume of the total space, volume of the space, they represent that we represent as volume of the voids by the VV. So I would say that total VV is only that part of the volume of air and volume of water. This is the total VV. So VV is actually volume of air plus volume of water. That's the total air. That is the total space we have, except that of the soil particles, except that of the soil solid particles. So this is the total volume. So you can say this is the total volume of the soil mass, and you subtract the solid particles, that we can get the volume of voids. So this is the volume of voids. We write it as volume of voids, volume of voids, volume of voids. So this is your general three-phase diagram. This is your three-phase diagram. Three-phase diagram. Now, if I say that, that those all those voids are filled entirely with water. Now, first case is there. If the possibility is that if all voids are filled with, or all voids, I would say, if all voids are filled with water, filled with water, filled with water, that means the total volume of the voids is equals to volume of the water and volume of the air. But volume of air would be 0 because there won't be any air in the voids. All the voids are filled with water, so your volume of voids are replaced by volume of water. Now, if I want to represent it by phase diagram now, if I want to represent that by phase diagram, I would say you are having some solids, you are having some soil solids, and you are having some water, and there is no air. If there is no air, that means there is no volume of the air. So this total volume of the water, I would say total volume of the water is replaced by the total volume of the voids. And we have this one volume of solids. And from the side, I would say there we have weight of solids, and this is your weight of the water. And in this case, we say volume of air is equals to 0. And this case, we call it as fully saturated soil. Fully saturated soil. Fully saturated soil. That means that soil is fully saturated with water. That means all the pores, all the voids are filled with water. We call it as fully saturated soil. And in this case, we call it as two-phase diagram, because the air part is going to be blown out. That two-phase diagram, because there is no air, so we can't show that air. There's no volume for the air. There is no space for the air. So I would say we are only having water and solids. That we call it as two-phase diagram for the fully saturated soils. And one more possibility here, we can say, if there we have volume of void is equals to volume of air plus volume of water. Now, second possibility is there, if all the voids are filled with air, if all voids are filled with air, that means no water is present inside the soil mass. That means water present is equals to 0. Water present in the voids is equals to 0. Water in the voids is actually 0. So that means volume of the water in the voids is equals to 0. So that we call it as a dry condition. That we call it as a dry state of the soil. Dry state, dry soil. We can call it as a dry soil. And to represent in terms of phase diagram, I would say we're having some solids and we are having some air, and there is no water. There is no water. That means there is no volume for water. There is no volume for water. That's why this is also two-phase diagram. This is also two-phase diagram. This is also two-phase diagram, and we can show those parameters. I would say this is your volume of the solids, and this is the volume of air. Your volume of air equals to volume of voids. And if I talk about in terms of total, this was your total volume V. So our volume of V is actually volume of air plus volume of solids in this case. And from this side we can say there is some weight of air, and weight of air is actually 0, and we have some weight of solids, and this is not 0. So finally your total weight, if I say that total weight of the soil, that is actually equals to weight of the solids here. So total weight of the soil, soil mass is only contributed by the weight of the solids. So we can say your dry weight, this we also can write that dry weight of the soil. This we can write dry weight of the soil. Dry weight of the soil mass. Dry weight of the soil mass is actually equals to weight of the solids. Weight of the solids only. Weight of the solids. So actually this is the criteria we got. The dry weight of the soil mass is actually weight of the solids only, because there is no water. So air is also having 0 weight, so weight of the solids is equals to dry weight of the soil mass. So this is the second case, second possibility we can have. That's a two-phase diagram. Now we are going to have few definitions, and these are your important tools for your geotechnical engineering. So that we can write here definitions. Let's write that definitions. So first important definition, we write water content. We write here water content. It's represented by small w. We can show it in this way. Water content to differentiate with other weights. To differentiate it with other weights, we write it as a small w, and that curved part, water content. That's actually the ratio of weight of water. That's actually weight of water. It's a ratio of weight of water in the soil mass divided by the weight of the soil solids. Weight of the solids, we can write. So I would say this water content can be, it is actually equals to weight of the water divided by weight of the solids. This is the weight of the solids, not the soil mass. Weight of the soil mass is actually capital W, and weight for the soil solids is WS. Okay, so this is your water content. Now there might be possibility that we might be having some water. We might be having some water if the case is that dry condition is there. If the case is that we have a dry condition, at that time your water content would be 0, because weight of the water is 0. That means water content would be 0 at that case, if the case is dry. And there might be also possibility that if you have this one of the soil particle inside that infinite number of water, infinite volume of water, we have one soil particle, we have one soil solid particle. One solid particle is there inside the infinite volume of water. That means we can say we have infinite number of water, infinite weight of water, and we have less weight of soil. That means this is almost we can say this can be also greater than, this would be greater than 0. So but actually the soil won't be in this way that we have one soil particle in infinite volume of water. We're not going to say that. So but for actual sense would not be that, but to say that your water content can be have a value such that it can be greater than 0 or it can be equals to 0. So in this case water content was 0, but all other cases we can have water content greater than 0. So this is your general results for your water content, that it can be either 0, or it can be having any other value greater than 0. So this is your water content. First definition, that's your water content. Okay, second one is here. Second one we can have that we call it as void ratio. We call it as a void ratio. Void ratio that we represent as E, small e. So this is actually volume of voids with respect to the volume of solids. With respect to the volume of solids, you are taking that soil specimen. Some soil specimen is there, soil is there. It's having some volume associated with that voids, and there is some volume of solids also, such that total volume is equals to VV plus VS. And from that we define that void ratio, that is the ratio of volume of voids divided by volume of solids. Now from this case, I would say there is definitely going to be some value of voids. There is definitely going to be some value of voids always. It can't be zero. Your void can never be zero. It's never zero. Your void is never zero. That means if there is some void, there would be some volume of void. So it would be never zero. That means its value is always greater than its value is always greater than zero. And if we talk about fine grained soils and coarse grained soils, FGS, I write it as FGS, and we have coarse grained soils, coarse grained soils, coarse grained soils, CGS, CGS. In short, I write it as FGS, CGS. So can you tell me that what is the void ratio relation here? What is the void ratio for FGS and what is the void ratio? It's greater than or it's lesser than? I would say your void ratio for fine grained soils is actually more. That means the voids, if you take a particular unit of volume for fine grained soils, fine grained soils, we're having more number of voids, more volume of voids is there, more volume of voids, more volume of voids. If I take that total volume of the soil is 1 meter cube, in that we are having some volume of solids, and we are having the volume of voids actually more. With respect to if I take that same volume of 1 meter cube, but the soil is actually coarse grained soils, coarse grained soil is there. Here we have more volume of solids, but we have less volume of voids. Volume of voids is less as compared to that. Because of that, we have void ratio that's greater than that EFGS is greater than ECGS. But one more term is there that we call as void, size of void. But size of void is actually bigger. So size of void is here in the what you call as fine grained soils is actually lesser than in case of CGS. So here we have that void. This is the void space. So this is the size of void. This is size of void. But if you talk about this one, we have infinite number of those soil particles. And if I say that what is the void space, what is the void space, I would say this is your void space. This part is your void space. So your void size of the void is actually less. Size of the void is actually less. But void ratio, this is a different term. Void ratio is not void size. Void size is different thing, and void ratio is different thing. Okay. Void ratio for fine grained soils is greater than for coarse grained soils. And similarly, we can have in this case that water content, we can have more weight of water. We can have more weight of water in the fine grained soils as compared to the those coarse grained soils. So based on that, we can say water content for fine grained soils is actually greater than water content for coarse grained soils. I can say that from this perspective, because we have more voids, that means we can have more water present in them. Okay. Now third parameter, third definition, third important tool that we call it as porosity. That we call it as a porosity. This is the third part. Third definition, porosity. We write it as small n. That is actually volume of voids with respect to total volume of soil. So this we write it as n equals to volume of VV by V total. VV by V total. So this is volume of voids with respect to total volume of the soil mass. Yeah, this we have to write here soil. Volume of soil mass. So, but the previous one was void ratio. That was ratio of voids with respect to volume of voids by volume of solids. And in this case, this is volume of voids by volume of soil mass, entire mass of the volume, that soil mass. That we can also say this is I can say this, if I multiply it with 100, I can get that percentage voids I can write. This is also, we can call it as percentage voids. This is the how much percentage of the total volume of the soil we are having that total percentage of that voids. This is the total percentage of how much total out of the total volume, how much percentage we are having voids. That's percentage voids. That is represented by porosity. porosity. And it can say, we can say, if there is some soil, if there is some soil, if there is some soil, so I would say total volume of the soil is actually volume of solids plus volume of voids. So if there is some volume of solids always, that means your porosity is never greater than 100%. Your percentage void is never 100%, greater than 100%. So this is your criteria. Now final statement is there. Final statement. The comparison with of that n versus e. Comparison of n versus e. This is the one conclusion. N versus e. Which one you are going to prefer for your engineering perspective of that soil, which you are going to use in a decent way and in a suitable way. If we talk about that porosity, porosity is accounting that total volume. If you check the denominator, it's having the total soil volume. But if you talk about the that void ratio, it says that I am having that denominator of volume of solid is only. Volume of solid is only. Volume of solid is only. Then we say that because that volume of that total volume is a function of volume of air, volume of water plus volume of solids, but your volume of solids is only a function of volume of solids. And we say that your air is compressible. Your air is compressible. If the air is compressible, so we can decrease the voids of air. We can reduce the volume of air. If there is water, we can say water is sometimes, we can say this is also some sort of compressible, or we can say this is also, let's talk about this is incompressible. Let's say that this is incompressible. But if there is air, so your total volume is going to change. Total volume is going to change. If there is total volume going to change, that means this parameter is the value of n is also going to change. So n changes with as v changes, n is also going to change. If the value of n changes, your v is also going to change. So, but if you talk about the void ratio, it's only accounting what you call as volume of solids. So we say solids are incompressible. So that means volume of solids is not going to change. This is not going to change. See the top, n is equals to vv by v, and e equals to vv by vs. So we are comparing the denominator, that which one should we prefer for all other parameters to calculate. So here we have, this part is going to change, this is going to change, but this part is not going to change. So better option is that we should prefer void ratio for those parameters to calculate that we are going to see in the later case. So I would say better option is that you prefer void ratio. Because it accounts that volume of solids only, so such that it's not going to change with the time. So we can write that statement. Why we prefer void ratio. So your E is useful parameter than E, then N. It's a useful parameter than N for representing volume changes, volume changes under compression. That we say that's consolidation, that is compaction. We are going to see that later for volume changes under compression. Okay. Now one more term is there that we call as degree of saturation. Degree of saturation. So that we represent as capital S. So this is the actually ratio. This is the ratio of volume of water. It's talking about the saturation that's related to water. So out of the total volume of the voids, how much percentage of the voids are filled with water? That is the volume of water divided by volume of voids. Okay. So now the possibilities are there that this is the volume of water by volume of voids. Now if I talk about dry condition, if the soil is dry, at that time your water is there. If the water is not there, that means volume of water is equals to 0. At that time your volume of water is equals to 0. At that time your saturation is actually 0. So it's actually dry soil. That means there is no saturation. No void is filled with water. It's not saturated with water. So we can say this, it's your dry soil. Volume of water is 0, such that S is actually 0. Now one more case is there. If we talk about fully saturated soil, in that case, your entire voids are filled with water. Your entire voids are filled with water. That means at that case, your volume of voids is actually volume of voids. Your volume of water is actually total volume of voids, and you have this ratio equals to 1, or we can say 100%, 100% degree of saturation at that case. Okay, this is your saturation, degree of saturation. After that, we have percentage air voids. Percentage air voids. We write it as percentage air voids. So here the name suggests that we have how much percentage of total volume, how much percentage of total volume is actually filled with air. That is the volume of air. That is the volume of air divided by total volume of soil. Volume of soil mass. Volume of soil mass. So that we can represent it as Na. We write it as Na. We can write it as Na percentage air voids. That is the volume of air divided by total volume of the soil mass. After that, we have air content. We can write, we have air content. Air content. We have air content. So this content means it's the ratio of volume of air divided by volume of solids only. Yeah, volume of voids only. Volume of voids only. Voids, volume of voids. So this is the air content is represented as AC. So this is equals to volume of air by volume of voids. So we can write volume of air divided by volume of voids. Volume of voids. After that, we are going to talk about that unit weight. Unit weight. Now the terms are related to a unit weight. Unit weight. So you might be knowing that what is density? What is density? That's mass per unit volume. Mass per unit volume, kg per meter cube. Now, if I multiply that that density with this is we call it as density. If I multiply that density with gravity g, if I multiply that with g, I would get that m times g divided by v. So this is actually initially this was mass in terms of kg. Now we are getting weight. This part is weight now. This is weight in terms of some kilonewtons, in terms of some newtons, in terms of some kilonewtons divided by that meter cube volume. So this is actually weight per unit volume. So this part rho times g we write as gamma. So this is your unit weight, gamma. So we have different names for that unit weight. Let's go for those different names. First one, that's we call it as bulk unit weight. Bulk unit weight. Bulk unit weight. So let's write it as we sometimes write it as gamma t, and sometimes we can write it as gamma bulk. So I can say gamma bulk is actually weight of the soil mass, total soil mass divided by the volume of total soil mass, divided by total volume of the soil mass, volume of soil mass. We are having some soil, it's having some weight, and we are having some soil, it's having some volume. So that's your ratio. That's we call it as gamma bulk unit weight. After that, we can say we can also say there is one more term, that's unit weight of solids. Unit weight of solids. Unit weight of solids. Let's write that. Unit weight of solids. Second one, unit weight of solids. And this one we can write it as gamma s. That's related to solids. Whenever there is s, that means it's related to solids only. Gamma solids. So this would be related to solids. So I can write weight of the soil solids. Weight of the soil solids. Soil solids divided by volume of the solids. Volume of the solids. We are talking about soil, so we can ignore that soil. So I would say weight of the solids by volume of the solids only. So this is, you can highlight this part. We are writing only here. That means we are talking only about the particular volume the weight of the solids are having. So this is your weight of the solids. Let's write here. This is equals to weight of the solids by volume of the solids. So this part we also call it as absolute unit weight of the soil. Absolute unit weight of the soil, because this part is not going to change. Never this part is going to change. This is absolute unit weight of the soil. Absolute unit weight of the soil. Unit weight of the soil. Because your weight of the soil in a particular volume, if you take a particular volume, of the soil, it's having a fixed value. It's having a fixed value of weight of the solids. It's not going to change with time. Weight of the solid is not going to change, and there is some fixed volume of the total. There is some total volume of the soil, but it might change under time. It might compress because there is air. It might compress, but the volume of the solid is never going to change. So based on this one, we say this is your absolute unit weight. Also, we can say this is your absolute unit weight of the soil, but it is actually unit weight of solids, unit weight of soil solids. After that, we can have we can talk about water also. You might be knowing that. What's the unit weight of water? Unit weight of water. Unit weight of water. So we can say this is the weight of water divided by volume of water. Weight of water by volume of water. What is the weight of water and what is the volume of water in a particular? Let's take that you have particular volume of water in a container, and you would say what is the total weight we have in the water and what is the volume occupied by that. So that's your gamma water, gamma W. And its weight is generally, its value is generally taken as 9.81 kilonewton per meter cube. And this value, we say that gamma W is a function of temperature. So this value is taken at a specific temperature of 4 degrees, at 4 degrees Celsius. As it's also a function of temperature, sorry. So that's your gamma W. After that, we can take gamma dry. That's, we can write dry unit weight of soil. Dry unit weight. That's related to soil. Dry unit weight. We can write it as gamma D. This is the weight of the soil in the dry condition. So first one was that bulk unit weight. Bulk unit weight was the weight of soil in actual condition, that you take any particular amount of the soil, and you are saying what is the weight of that particular soil mass and what is the total volume of the soil mass in that actual condition it was having. We are taking it from the field, so we can say this is your actual field condition, that we call it as bulk. After that, we can have this condition that we write it as dry unit weight. So this is also weight of the soil, but it's under the dry condition. So when we have dried that soil specimen, so after that we are saying this is your gamma D. So weight of soil in dry condition divided by total volume of the soil. Volume of soil in that dry condition. So we can write it as gamma D is equals to gamma dry of the soil divided by volume of the soil. But we also know one thing. We know one thing, that if the soil is dry, that means there is no water. Only there is solids. There is solids and there is air. And weight of the air is 0. So your total weight of the solids, total weight of the soil solids, total weight of the soil, that we have dry weight actually, and this is actually only equals to weight of the solids. So we can say this is also equals to gamma of the solids. Weight of the solid is divided by volume of the soil. So here the difference we have, if you compare this one with respect to unit weight of the solids, what was the equation? So this was your unit weight of the solids, that was Ws by Vs. But in this case we have Ws by capital, that total V. This is total V. So this would be lesser than gamma S. Because in that case, because in the gamma S we have divide off Vs that was less than total V. So this is that extra part we can have. So this is your gamma D, that is dry unit weight of the soil. This is the total dry weight of the soil mass divided by total volume of the soil mass. But your total weight of the your total dry weight is actually your weight of the solids, and divided by that, I would say total volume of the soil mass. Okay. After that, we can have gamma saturated. We can have gamma saturated. We can have gamma saturated. That is saturated unit weight. So one more unit weight is there, that we call it as saturated unit weight. Saturated unit weight of soil. So that we write it as gamma sat. Gamma sat. So that is actually saturated weight of soil. Saturated weight of soil. Or we can say soil weight of saturated soil. We can also say this is such weight of saturated soil, or we can say that is saturated weight of soil. After that, let's write it as a specific term, that weight of saturated soil. Okay, weight of saturated soil. Weight of saturated soil divided by total volume of the soil, divided by volume of the soil, volume of soil mass. Soil mass. So we can write gamma sat equals to saturated weight of the soil divided by volume of the soil mass. Gamma sat. After that, we have final unit weight that we call as submerged unit weight. We have submerged unit weight. Final one, that's submerged unit weight of the soil mass. Unit weight of the soil mass. So all these are related to the soil. All these unit weights are related to soil mass, except that gamma solid that was related to gamma solids, that was related to solids only. So these are all others are related to soil. So gamma submerged, I can write here gamma submerged, or we can also show it at gamma dash, that to say this is also gamma submerged. This is actually the ratio of, this is the weight of submerged soil, and divided by total volume of the soil mass, particular volume of that soil mass. So this we can say this is your gamma submerged, or we can write this is gamma dash, that's gamma, I can write this is the weight, this is submerged weight, or I can say this is gamma dash, W dash, divided by total volume. This is the equation. And this means that your soil is submerged inside the water. That means soil is placed inside the water. And because of that, we'll be having that one concept of buoyancy. So there will be some buoyant force acting on the soil solids. So buoyant force will be acting on what we call as soil solids. So your solids are having some volume of solids. So on that volume of solids, we are having that buoyant force FB, and because of that, your weight of the solids is actually now lesser. Your apparent weight will be lesser. Your apparent weight of the solids would be lesser. Now, based on that, I would say your gamma sat, we also write it as your equation for the gamma submerged is equals to gamma dash is equals to gamma saturated minus gamma W. Gamma sat minus gamma W. Based on this concept, we derive it in this way, that we have this equation for that. Okay. So I think this is the end of that definitions related to that geotech. So these are the important definitions and important tools that would be that entire geotech is all about these parameters that we calculated, that we have. After that we have few more. We forgot. We have a few more that's related to specific gravity. Now these ones are related to specific gravity. Now once we got the gamma, once we got the unit weight, Now we are saying what's the specific gravity. That's we write it as G. So this is a G. That is actually the ratio of unit weight of one material. Let's say that unit weight of soil, unit weight of soil divided by unit weight of standard fluid, unit weight of standard fluid. And in our case, we take that standard fluid. We are talking about water. So we say that unit weight of soil, divided by unit weight of water. So that's your G, specific gravity. Now we had different, based on the gamma base, we have different unit weight, we have different specific gravities. Let's talk about the first case, that we our first one, we call it as absolute specific gravity. First term is there. This is the first one. That's absolute specific gravity. Absolute specific gravity. We also call it as grain specific gravity. It's talking about only those grains, solid soil solids only. That's why here we also call it as absolute. Grain specific gravity. Grain specific gravity. And this we write it as actual. We can ignore this part now. We can ignore this part now. We can ignore this part now. You can say this. We also we write it as capital G, or we can also write it as GS. That's your specific gravity for the soil solids. So that's your absolute specific gravity. So that would be the ratio of unit weight of the soil solids divided by unit weight of water. So this is your unit weight of soil solids. Unit weight of soil solids only. And this is the ratio that, so finally you can write G equals to gamma S by gamma W. We then generally write it as in this way. Okay. After that, there is one more, and there is one more. From this we can have one more part here. What is actually gamma S? What's actually gamma S? Can you tell me what is gamma S? That's actually weight of the solids, by volume of the solids. And what is gamma W? That we can have, this is gamma W. So then finally, sometimes we can have equation for the what is the weight of the solids. We can convert it in this way, that weight of the solids is actually specific gravity of the solids into G gamma W into Vs. G gamma W Vs. This is one more equation for the weight of the solids. This is important tool that's used frequently in calculations. Okay. After that, we have mass specific gravity of the soil. Second one is there. We call it as a mass. This one is your general value. Mass specific gravity of soil. Specific gravity of soil. So this we write it as GM. That's related to mass. That's a general value, bulk value we can write. GM, that's unit weight of soil. Unit weight of soil divided by unit weight of that water. And this unit weight, we are talking about bulk one. Bulk condition, so we can write it. This one is your GM equals to gamma bulk by gamma W. So this can be any condition now. Now depending on the value of bulk, it can be now gamma dry, it can be now gamma submerged, it can be now gamma saturated. So we have different conditions for that bulk value. Okay. One more condition here, one more term, we call it as relative density. So this will be touching in other chapters also. This one is your relative density. Relative density. This is, we write it as dr. That is the ratio of void ratio, maximum void ratio we can have, minus void ratio of the field condition. This is the actual field condition of that soil mass. This is the void ratio of the field condition of the soil mass divided by maximum void ratio we can have minus minimum void ratio we can have of the soil mass. So we are having some soil. This is some soil, and what is this Emax mean? Your Emax corresponds to, this is the void ratio. Void ratio at, that means void ratio is maximum. That means volume of voids are more and volume of solid is less. That means it's talking about the loose condition of the soil. Loose condition of the soil. So this is talking about the loose condition of the soil, and this is performed. This is calculated in the lab. So this is the lab test to calculate the Emax of the particular soil. This is done in the lab. After that, we have E minimum. That's we call it as minimum void ratio. Void ratio at void ratio at, that means our void ratio is max, that's the minimum possible value of the void ratio for that particular soil. That means we are having the, this is the maximum. That means at this condition we have minimum number of minimum volume of voids. We have minimum volume of voids. That means more solids are placed inside particular volume and less number of those voids are placed. That means we can say this is in the compacted condition. This is in corresponding to compacted condition. So here we can write it's corresponding to compacted condition of the soil. So I would say at the rate of Emax, we are having we are having minimum gamma weight of the soil, and at the rate of minimum void ratio we are having maximum unit weight of the soil, because we are having more solids placed inside that particular volume. It's at that loose condition, that means minimum unit weight. At this compacted condition we have maximum unit weight of the soil. After that, this one is your E field. E field is your actual, you are taking a particular soil of that same character, you are taking that soil in from the field, there might be some value of water content, there might be some void ratio. This is your E field. That means your, what's the actual value, what is the actual field value you have, actual field value, actual field void ratio we can write here at the rate of actual, gamma field, at the rate of actual gamma field. So this term we are using, for actually we are using this term generally for cohesionless soils, and cohesionless soils we include them as sands and gravels, not clays, not solids. So this one is your cohesionless soils. This is an important parameter useful for those, and this is more useful. It's more useful. This is more useful than E for these kinds of soils. More useful, I can write here. And this from this dr we sometimes we compare that those, we have the category of those soils based on the values, of dr, based on dr values, relative density values. We sometimes have the categories of soils also. We classify the soils in this way, that if your value of the dr is in the range, if your dr value is in the range 0 to 15, and 15 to 20, 15 to 35, 35 to 50, yeah, 35 to 65, 35 to 65, 65 to 85, 85 to 100. And accordingly, we classify the soils as, your soil classification becomes that very loose. This is very loose. After that, we have loose. After that, we have medium dense. After that, we have dense. After that, we have very, very, very dense, That means your cohesionless soil is having, if your value is some say some value around 65 to 85, that means your cohesionless soil is in a dense condition. That means more. If your value of dr is more, it means you are approaching to the maximum value of density. Your density would be more in the field condition. Because your ratio Emax minus Emin, Emax minus E field divided by Emax minus Emin. So this part is maximum value. Let's say this is some value of, let's say this is some value of let's talk about, let's say this is some value of 10. And if your, this is the minimum value we can have related to the void ratio. Now if you got the field ratio, if you got the field void ratio also close to this value, that means you got that dr equals to 10 by 10, that means one value. So your that means your actual field value, of the void ratio, that means your actual field value of the void ratio of the that your actual void ratio for the field condition of the soil is almost equals to minimum void ratio. And when there is minimum void ratio, at that condition your gamma is maximum. So it's actually saying that your dr is a function of density. If your dr is almost 1, that means your density is in the maximum possible value, it's around the maximum possible value. So this parameter is generally used for cohesionless soils. Yeah. Yeah, this was the end of those important definitions. After that, next lecture will be related to the relationships we are going to derive based on these important definitions after that. Thank you for watching that. Thank you.